Yeah, thanks very much to the AIG for the opportunity to present today. It's a real pleasure, and a big hi to everyone, and thanks for attending wherever you may be joining in from. My talk is about breccia pipes and intrusion-related copper deposits from Latin America. I was hoping to present something that might be a little bit different and perhaps some new ideas and concepts about this subject. So the cover slide is from the La Playa district in southern Ecuador. It's pretty obvious where the Tourmaline Breccia is. So the presentation outline, I've got a few comments about Tourmaline Breccias, their textures, the mineralization, and some of the examples I'll talk about simply because of time constraints. I'll focus mainly on two, which are in Peru and Argentina, and projects that are currently being explored by Chicana Copper and Tourmalina Metals. I have some concluding remarks, and I would like to acknowledge both Chicana and Tourmalina for permission to present some of this data. I would also like to acknowledge the project geologists working on both of these projects who have managed to keep the rigs turning right throughout the winter, in addition to which having to deal with all of the constraints and issues concerning COVID. Most geologists are fascinated by breccias. Me personally, I have throughout my career, and I find them extremely intriguing, and especially tourmaline breccias. Over the years, I've been fortunate to see a large number of these, and so much of what I'm presenting is actually based on field observations. If one reviews the literature, there's an awful lot being written about breccia pipes, but actually not that much specifically about tourmaline pipes. And so what I've done here is just made a compilation of some of the papers I think are most relevant. And also I've made a comment about aspects in the paper that I found useful. Obviously, anyone that's interested, you can look at this at your leisure later. So one of the first papers that actually highlighted some of the features in breccia pipes was that by Emmons in 1906, who studied the Pilares deposit in Sonora, Mexico. And in that, there were two things that came out of his paper. One was descriptions of the textures, which on the top right is a great example of decompressive shock, and I'll talk a little bit about that later. And on the bottom right, if you look at the distribution of the workings, you can see that the workings followed a semicircular pattern, which actually was the margin of the breccia pipe. But the paper I really enjoyed most and found incredibly good and descriptive was that by a geologist called Walter Weed, who was working for the USGS back in the time of Emmons, etc. And he published a fantastic paper based on his work at Copper Creek in southwest Arizona. When I started looking into his career, I found that he'd published a lot of very good papers, and he was truly a wonderful field geologist. And I'd say he was right up there with Emmons and Lindgreen. And you're no doubt wondering who the lady is on the right. Walter was married to a geologist, and she was involved in the early suffragette movement, and she made some inappropriate remarks in a court case, and for that she received 2 nights in jail. So one would expect that the male geologist might be in jail for insider trading or salting samples, but in this case it was the wife. So here are some of Weed's observations that he published on Copper Creek. Copper Creek literally has hundreds of breccia pipes in a relatively small area of a few square kilometers. Not all of them are tourmaline pipes, but many of them are. And so I've highlighted here the key points, and this really, it's almost a checklist as to things that you would want to look at if you're assessing hydrothermal breccia pipes. So he outlined that there were many in a small area. He understood that they form prominent craggy outcrops. He alluded to the underground mining, which showed that the best mineralization was typically around the margins. And he also had good descriptions of the textures, and he compared some of the textures he saw to those that had been published slightly earlier at Pilates. He also noted that the breccia contacts were sharp. He noted sheeted veins outside the contact, and he also noted some of the paragenesis and multi-element nature of the pipes. But one of the models that has influenced my thinking greatly was that published by Chris Halls some time ago. And Chris had studied mainly the Wheal-Remfry pipe in the Cornwall district in southwest England. And so what Chris had published that really caught my attention was the initial concentration of the volatiles and fluids in the cupola, the influence of pressure, and also the actual 3D geometry of the breccia pipe. This is just really a modification of Chris's model, and I'll point out here that this applies mainly to pipes I've seen that are not directly associated with the giant porphyry copper deposits. They're a lot more complex. For example, Los Sulfatos. I am working on a model, but it's much more complex than this simplistic model, which basically attempts to portray how tourmaline breccia pipes form, bearing in mind not those that are the giant ones. So on the left, we have a buildup of volatiles and fluids in a cupola, and the green shows a Hornfels carapace, and the red arrows relate to volatile pressure and lithostatic load pressure. So in the early stages, we have a buildup of volatiles and fluids confined in a cupola. And then to the middle, as the volatile pressure increases significantly, the wall rocks above the cupola start to fail, and the volatiles, mostly volatiles, and some fluids escape into the wall rocks. And finally, the volatile pressure comes into equilibrium essentially with the lithostatic load pressure at the time of the formation of the main breccia pipe and precipitation of the mineralization. A very simplistic model showing the features that one can recognize in cupola rocks. High silica carapaces or silica accumulations. This is magmatic. USTs, which are unidirectional solidification textures that are magmatic segregations of quartz, marilitic cavities, and pegmatitic lenses. For the purposes of this presentation, I'm only going to talk mostly about USTs and a little bit about the high silica. I just don't have time to discuss the rest at the moment. So here's an example of a quartz tourmaline segregation in a cupola. This is at Roach Rock in southwest Cornwall, and it's just simply a mass of tourmaline and quartz. But what's really important are the USTs, or unidirectional solidification textures. And so this is actually the first recognizable event that I can see in the formation of a tourmaline breccia. And as you can see, it's not even a breccia, but it is it's a cupola texture, and it's subparallel bands of quartz and tourmaline, which are formed by fluctuating overpressure in a cupola. And so this is evidence for the buildup of the pressure prior to the formation of the main breccia pipe. And so this is an example from the Bayan Ul district in central Mongolia, where there are many breccia pipes. And this represents the first phase with very obvious USTs, quartz tourmaline USTs, so that at this point, the volatile pressure is just starting to build up, but everything's confined because of the much greater lithostatic load pressure. And so as the volatile pressure increases and starts to overcome the lithostatic load pressure, the volatiles and fluids begin to escape into the overlying wall rocks, and we have an overprinting fracture and vein network of volatiles and fluids into the hydraulically fractured wall rocks. And then finally, as the volatile pressure greatly exceeds the lithostatic load pressure, we have the main breccia pipe formation. Not all tourmaline breccia pipes are mineralized. In fact, probably the majority of them aren't, but they do show the same features whether they are mineralized or unmineralized. And so here's a really nice exposure of quartz tourmaline USTs in the Bayanovo district in central Mongolia. Outcrops elsewhere in the region show most of the features that characterize tourmaline breccia pipes, including shingle clasts on the top left, decompressive shock, fluidization textures on the top right, and USTs on the bottom. The type location for those interested in tourmaline breccia pipes, and it was where Chris Halls did his seminal work, and to a certain extent myself many years ago, is the Will-Remfry deposit in the clay districts of southwest England in Cornwall. And so at the time, there were beautiful exposures of the Will-Remfry pipe, and you can just simply see the color contrast there, which shows where the pipe is and its contacts. And it's possible to walk along the bench from outside the pipe, across the contact and into the pipe. And when one does that, you can see that as you walk from the wall rocks and you approach the pipe, you pass a very diagnostic sheeted vein or sheeted fracture section, and then you hit the tourmaline pipe with a very sharp contact, and then you're into the pipe. What one sees in the sheeted fracture zone are, as you would imagine, is subparallel to parallel networks of sheeted fractures and veins filled with tourmaline and or tourmaline plus quartz, and some really nice examples of hydraulic fracturing. As you come to the actual contact of the breccia pipe, and typically breccia pipe contacts, at least of this type, are extremely sharp. You can literally put your finger on the contact. So it doesn't take much imagination to see that how you would develop shingle breccias if the pipe starts to expand into the sheeted fracture network in the wall rocks. And so what the shingle breccias represent actually were formerly a sheeted fracture zone in the wall rocks. There are several examples of this that are in the literature. There's a really good paper by Silito and Sawkins from way back. They observed the same sheeted zone in the margin and then passing into slab-like fragments in the breccia. And curvilinear clasts are also diagnostic, and these I refer to as decompressive shock features. Here are some nice examples from Will-Remfry, and basically these are a product of what looks to be a drastic drop in the fluid volatile pressure, and it's essentially a rock burst. And so when you see these textures, it's pretty good evidence for drastic drop in pressure, because what you can actually do visually is essentially reconstruct the clasts into one basic mass. Here's also some quite good examples, and especially the one on the right, which is from Will-Remfry. And you can see that the larger clast there can easily be reconstructed into one wedge-shaped clasts before the sudden drastic drop in pressure. Fluidization is another characteristic texture that is seen in a lot of hydrothermal breccia pipes, and particularly tourmaline pipes. And really all that is illustrating is high fluid pressures and a great deal of mixing in the central part normally of the breccia pipe. So one typically sees rounded to sub-rounded clasts, quite often mixed clasts, different size clasts, and a lot of rock flour can sometimes be present, and also typically a high matrix to clast ratio. This is also from Will-Remfry, and this particular clast has, it was a originally in the wall rock, where you can see sheeted veining and fracturing, and this became incorporated into the central part of the wheel Remfry pipe. Another example, which is a good one, of decompressive shock is from the Yabrakoya district, and this slide was kindly given to me by Greg Corbett, and it's a great example of decompressive shock. Most tourmaline pipes and a lot of other breccia pipes are typically oval in plan as opposed to circular. And one explanation for this may be that the long axis of the pipe often parallels the dominant structural trend. There could be other structural settings for this, but to me, this seems to be an obvious one. What I'd like to show here is how breccia pipes, tourmaline pipes, can evolve. And I think this happens very quickly, so that on the left, we're starting to initiate a pipe. And then, as we saw earlier, as the pipe expands, we incorporate the sheeted vein zone around the previous pipe, and that becomes a shingle zone inside a rapidly expanding pipe. And I think this happens fairly quickly, relatively speaking. It's important to understand where the best mineralization is often occurring around tourmaline pipes, and this applies to some other pipes as well. And it's typically at the lobes or the margins. And there's a very good reason for this, and I think it's to do with the original sheeted vein zone surrounding the pipes. And at the lobes of the pipes, this becomes quite a complex structure, and the actual sheeted fractures and later shingle clasts don't stack very well together. And so this becomes a highly permeable zone, and obviously a favorable locus for mineralization. And so it's important, I think, to understand where the best mineralization might be concentrated. And in many cases, this is at the margins and particularly at the lobes of pipes. And it's all to do about permeability, because at those lobes is where it's the best place for open space and deposition of mineralization. Some examples of this, this is the Los Pilares mining district in Sonora, Mexico, and it was where Emmons originally published his work on breccias. This was one of the founding copper mines of Phelps Dodge, actually, and you can see where the yellow arrow is, the very prominent outcrop that I commented earlier that tourmaline pipes often have, hence the name Pilares. But this was a very significant copper mine, and it was one of the founding mines of Phelps Dodge. Much later, John Tomes did some work on Pilares, and he published quite a lot on the geology. And one of his figures showed the distribution of mineralization on one of the levels. And it's very obvious where the best grades are around the margins and specifically the lobes. Pilares in the upper levels was 16.6 million tons at around 2.5% copper. And I think actually a lot of the pipe had been eroded off, and maybe there's still potential at depth. So in real terms, the overall resource could have been significantly bigger than 16 million tons. This is from a paper by Wade and Wanke, and it illustrates much the same thing. What I found interesting was, though, that there were other parts in the central part of the pipe which also had high grade. It shows that the top 300 meters was where most of the mining activity took place. And we see there some really nice shingle textures. There was a very good intercept just recently from the Soledad project in Peru, which is Chicana Copper's flagship project. And you can see here an intercept that was absolutely spectacular. It's 12 meters of 27% copper with significant silver and some gold. And looking at the core there, it's almost massive chalcopyrite. This occurs, as you would expect, right at the margin of one of the pipes. So this is exactly where you would want to be looking. So this is some more core from the Soledad project and one of the pipes. And what it also shows is very nice mineralization developed in shingle textured breccias in the upper part of one of the pipes. Some other examples. This is from a deposit in South Korea that I visited a long time ago. It was still operating at the time. It's called Il Kwang. It was a relatively small copper, high-grade copper tungsten pipe, and much the same story you can see from the contours on the left, the grade distribution and level plans. And the best mineralization was actually at the lobes and around the margin of the pipe. Some more examples from Soledad, massive chalcopyrite in the matrix, and quite often too in the class of the breccia, but generally speaking, the best grades are in the matrix. Oops, what am I doing here? Sorry. Yeah, so it's very important to know from an exploration perspective how to explore for the high-grade zones in tourmaline pipes, and quite often breccia pipes in general. And where you want to test are the margins and the lobes. So ideally, you would like to step back from the actual surface outcrop and drill through both sides of the pipe, rather than perhaps the temptation of drilling a hole down the center of the pipe. Breccia pipes typically occur in clusters. There's a few examples here on the right, and on the left are some of the pipes that have been recognized at Soledad in Peru. And you can see that there are many pipes within a relatively small area. There looks to be a broad zoning in terms of alteration assemblages associated with tourmaline pipes, as pointed out by Silito and Sawkins in their paper in the 70s. And so one progresses from essentially sericite tourmaline in the upper part of the pipe through down to tourmaline biotite, and at the lower levels, perhaps biotite and hematite. And I've also added quartz in there as well. So it may be possible to look at your alteration assemblages in addition to other textural information, etc., to determine at what level of the pipe you might be looking at. Breccia pipes and tourmaline pipes especially have very significant vertical extents, and this is often greater than 1 kilometre. In the case of Sursur, it's well over 2 kilometres, and some of the other pipes around Los Bronces and Los Helados, the vertical extents greatly exceed 1 kilometre, whereas the actual, in plan view, they can be less than 200 to 100 meters. So it's important to bear in mind that whilst the plan dimensions might be relatively small, the vertical extents can be quite large. I commented earlier about the topographic expression. Tourmaline pipes characteristically have very prominent topographic expressions. This is from one of the pipes, pipe 1 at Soledad, and you can barely make out a person there for scale, but very prominent topographic expressions. This is a photo taken from an aerial survey in south eastern Mongolia quite a while back, and even from the air it was extremely obvious what we were looking at. The black, of course, represents the tourmaline, and that you can even see copper mineralization associated with the pipe. So in many cases you can identify significant pipe clusters from the air. A great example of this too is also the Tourmalina Breccia mine, which is in central Peru. Very prominent outcrops. And also one of the interesting things about Tourmalina, in a paper from Carlson and Sawkins, again, you see the distribution of the really high grade around the pipe margin, and in particular, the lobes. It was from the publication, it was pretty obvious that the copper grades were significantly increasing with depth. This is a view of the Tourmaline area, and it was mined on several levels. And this is from the lower level. It's just an example of the mineralization where you see significant sulfides, chalcopyrite, pyrite in the matrix of the breccia. It's also interesting to note here that the clasts are basically rounded to sub-rounded, but it's monoclastic and they're all intrusives, which would imply that you were approaching the lower levels of the breccia pipe. So now to go into a little bit of detail about Chicana's Soledad project. It's located in central Peru. It's just south of Barracks Perinia gold mine, and it's in a very prominent district called the Aya mining district. There are many outcropping pipes throughout the area within a few square kilometers. And the history of this is that it was explored originally for porphyry copper systems. Quite often, companies use or tend to use the presence of Tourmaline Breccia pipes as vectors for deep porphyry copper systems. And I'll have something to say a little more about this towards the end of the talk. But the history of this was it was acquired and deep holes were drilled for looking for porphyry coppers, which was spectacularly unsuccessful. And so Chicana came in with the sole objective of testing the mineralized breccia pipes. And here's a close-up view of some of them. This particular cluster is from the southwest part of the property, a place called Companero. There are some extremely high copper and gold values in outcrop, and this pipe has yet to be drilled. So I think this will provide some excitement when the drills actually get to this part of the property. There's been a lot of drilling done over the last 2 or 3 years in the region, and generally speaking, there's been some outstanding intercepts. More recently, the drilling has been taking place at the Juan Carama cluster of pipes, and this is a drone photo that shows several of the pipes, and you can see there the drill rig perched on the side, off to the side of one of these. There's some really textbook stuff in the drill core, and so from the top we're going down the hole from left to right. So we pass through wall rock, through a relatively small sheeted vein zone. Often they're much bigger than that, into massive sulfide, into shingle breccia, and then slowly but surely into more fluidized breccias. So this is typical of what one might see passing from the wall rocks through the contact into the mineralized breccia. Some incredibly good examples of decompressive shock shown there. And some wonderful examples also of shingle breccias and high-grade mineralization. The mineralization at Soledad is polymetallic. There are places that are gold-rich and very high silver, combined with extremely good copper grades, as you can see there on the right-hand slides. This was one of their earlier intercepts quite a while ago, 44 meters at 7.8% copper, and that's what some of that material looks like. There are some places where there is very high-grade gold mineralization, up to 40 grams there, with high-grade copper and high-grade silver. More of some of the high-grade material, once again with high silver. Shingle breccias, lots of open space, porosity, and very good mineralization. Deeper in the pipes, at Chicana, they haven't yet found the bottom, or what the bottom of a breccia pipe looks like. Although what does seem to be happening, at least in 1 or 2 pipes, is that the amount of quartz is increasing, and the sulfide content is basically decreasing. And also there's a transition from in wall rock class composition from volcanics into intrusive clasts. So these textures here may represent the lower parts of what some of the solidad breccias are going to look like. This is 300 plus meters down hole. The only reason I've put this up, it shows the complex mineral paragenesis at solidad, and without going into it in any detail, when you look at the sulfide supersalt assemblages, it's really complex and it's very polymetallic. That's the main point. There's been some really nice work done in sorting out the stratigraphy at Soledad, and in particular, there's a very smart young Peruvian geologist, Victor Torres, who's doing an MSc at Codes together with Dave Cook on this project. And so throughout the mapping and drill core logging, the stratigraphy is becoming quite well known, and it's possible to plot the various breccias as shown there in the line diagrams as to where they are within the stratigraphy. And it's quite important actually to understand this, because where you want to be is at the higher levels of the pipe for the best mineralization. And this typically should be well outside the intrusive and in the upper stratigraphic units. It's also pretty obvious at Soledad that there's been quite a bit of erosion over the area post the formation of the breccia pipes. And so there's at least probably 1.5 kilometers of vertical extent at the Soledad breccia pipes. And so together with looking at the topography and where the mineralized zones might be, you can figure out which ones should be more prospective. So the higher you are in the stratigraphy, probably the better. Where you don't want to be is right down towards the bottom of the pipes. Also at Soledad, in many of the pipes, which is very common, as I will show a little bit later, the breccia pipes tend to be inverted cone shape. And so they increase in size with depth. The next project that I'll briefly talk about is the San Francisco de los Andes Tourmaline Breccia pipes, which is located in San Juan, Argentina. And this is currently the flagship project of Canadian listed company Tourmaline Metals. That's what the area looks like. There are literally dozens of breccia pipes in this area, and only one of which has had any real exploration and previous mining history, which is the San Francisco pipe itself. But there are dozens of unexplored breccia pipes throughout this district. This is the current camp that Tourmaline Metals have at San Francisco. On the upper right there, you can see where the old mine was. And in fact, I managed to find a photo of the old mine. This was formerly a bismuth mine. And so it was never really explored for anything else other than bismuth, but it certainly has significant gold and copper. In a paper that was published in 1969, Yambus and Malsavini, there was some very basic descriptions of the geology and pipe geometry. And what it showed was clearly a concentration of high-grade mineralization around the lobes of a pipe with relatively small plan dimensions. So we're only looking at probably 50 by 20 meters in plan at the current level of exposure. But what was subsequently found with drilling was that this pipe became substantially bigger at depth, which is basically what the model would predict. And so it also, the deeper drilling showed that there was significant mineralization way below the known old workings. So bear in mind the surface dimensions were relatively small, and it was well known for copper and gold, but some of the deeper drilling has actually located very significant mineralization at up to 400 meters below the present surface. So there's an intercept of 72 meters, 0.7 gold and 3.4% copper. classic shingle textures that are seen in the drill core together with decompressive shock, particularly the bottom one there where it's not difficult to reconstruct one clast in what became several clasts after being shocked, and curvilinear clasts as well, pardon me, as well. Some of the high-grade mineralization, what it actually looks like, mostly in the matrix, although there are examples of mineralized clasts, very nice grades. More of the high-grade material, and in some cases, almost massive sulfide, right at the margins of the pipe contact. Close-up example, really nice stuff. And in a similar vein to Soledad, at deeper levels, there appears to be a transition into more quartz-rich matrix and somewhat less sulfide. This is up to 480 meters downhole, and so there could be a transition. There are many pipes, as I mentioned, around San Francisco, and they're exposed at different levels, I think due to block faulting and erosion. And so it's actually possible to see what appears to be the base of some pipes. And one in particular, which is called Los Chorrillos, is essentially just tourmaline, strongly tourmalinized intrusive clasts, which are fine-grained and black, but they are intrusive. And the matrix is silica. And it's quite interesting because some of it is would appear to be USTs. And so this is what some of the outcrops around the Chorrillos Breccia pipe look like. And these would be interpreted to be the very base of some of the tourmaline pipes in the area. Other features that are seen around Chorrillos are some of the intrusives have sulfide tourmaline-filled mareolitic cavities, possibly orbicals and pervasive case bar alteration. So these would be interpreted as probably being the precursor mineralizing intrusives. Some more examples of around Chorrillos, close-up view of the mareolitic cavities with sulfides and tourmaline, and very high class to matrix ratio breccias. In fact, they're crackle breccias essentially. And so this would be what we think the lower parts or the base of some of the tourmaline pipes look like. Other examples, this is it's a real drill hole. It's a combination actually of drill holes, but it's possible to look at a series of drill holes and I think determine where you might be within the breccia column. And so the top right, we see quite nice sulfide matrix, relatively high matrix to clast ratio breccias with mineralization. As we transition down into the lower part of the pipe, the sulfide content has dropped off. It's monoclastic and it's mostly clasts. And then finally, towards the base, we come into essentially a crackle breccia in a mineralized intrusive that has disseminated sulfides. Tops of breccia pipes from elsewhere. This is an example from Mongolia, from the Bayanul district, where you can see that the class composition is essentially volcanics and it's a crackle breccia. This one is from San Francisco. The class composition are sediments and the crackles and fractures are filled with tourmaline. So this may well represent the top or the uppermost part of a breccia. It's also possible around San Francisco to see increasing degrees of crackle and tourmalinization, which of course would be a reasonable vector to where you might want to look for a blind pipe. An interesting example from the San Pedro de Cachayillo district in Inca del Oro in central Chile. And this was one of the deposits studied by Sillitoe and Sawkins, where they demonstrated what the fracture patterns above a relatively small tourmaline pipe can look like. And that's shown on the left, where you have a series of subparallel and concentric structures. And the diagram on the right is from Howard Colley's 1991 paper, and it shows approximately where the level of exposure is. This was a very good descriptive paper, actually, and it was possible to reconstruct the various textures. And it looks like in this particular case, the pipe is entirely hosted in the intrusion, and it's small and it was very weakly developed. So it never had a sufficient volatile fluid content to actually escape out of its host intrusion, precursor intrusion, into the overlying wall rocks. So, and in fact, most of the pipe in this particular case is not actually a breccia. It's probably better described as a crackle. I commented earlier about using tourmaline pipes as vectors for porphyries. It's an intriguing question. This is another example from Southwest Utah in the Cactus project, where tourmaline breccias were essentially considered to be vectors for porphyry copper deposits. And it really begs the question then, what is porphyry mineralization? I don't want to get into an in-depth argument or discussion here, but there's a couple of ways one could look at this, and it depends really what one's definition of a porphyry is. In my mind, the most significant porphyries are those that have evolved to fairly high levels in the crust. They've formed high-density stockwork quartz veins or breccias, and they have high-grade mineralization. Whereas on the left, there is mineralization in the intrusive. It does have disseminated copper mineralization, but it's probably been formed at quite a deep level in the crust and hasn't undergone or hasn't reached a sufficient level in the crust to form a more classical porphyry type system. And this, from Seedorf's paper in 2005, clearly demonstrates and nicely shows that most porphyries form within from 1 to say 3 to 4 kilometers in the upper crust. That's simply the main point for this slide. And so in that situation, we have nicely evolved porphyry systems, well-developed stockwork veining and or tourmaline breccia pipes, as shown on the upper right, this one being from Los Bronces. And the tourmaline breccias that form in the upper level of the crust consistently seem to have carrot shapes. And I think that's simply a reflection of the level of emplacement and the lower impact of lithostatic load pressure, amongst other things. Whereas what I term the non-porphyry copper deposits, meaning to say that the ones that haven't evolved into up to a high level in the crust, one could still perhaps call them porphyries, that's fine. But they form or tend to form at deeper levels in the crust, perhaps 4 to 8 kilometers in the upper crust. And they tend to have inverted cone shapes. And they often transition into low-grade, disseminated intrusion-hosted mineralization and or fracture controlled. Rarely do they have consistent or well-developed stockwork veining. And there was a nice study done some time ago by a PhD student in 1990 who studied a lot of the tourmaline pipes in the Western Cascades. And he was able to actually, having studied a number of pipes, which are shown there on the left, and place them into respective positions within the breccia column. It's a nice piece of work. If we move now quickly to the porphyry deposits, there's some really great examples, mostly in Chile, the Rio Blanco district, the Sur pit. From Fricken's PhD thesis, we see that the main breccia column there it's extensive, it's huge, and it's carrot shaped. Much the same occurs at Los Bronces. The breccias there. This is what some of them look like. What you note in looking at some of these rocks is whilst there's a lot of tourmaline, there appears to be an overall lack of some of the features we saw earlier in terms of well-developed decompressive shock and shingle textures. Anhydrite too is a fairly common component in what I call the porphyry-related tourmaline breccias from Los Bronces. Some of what the breccias look like from there. Very high grade and fantastic looking rocks. This is a plan that shows Los Sulfatos surface expressions of the tourmaline breccias. The significant thing to note here is the sheer size. The tourmaline breccias are orders of magnitude bigger than in fact, all of the other, what I would call non or polymetallic porphyry breccias that don't seem to be related to highly evolved porphyry systems. Some of the Los Bronces core, Alan Wilson kindly sent me this slide. Fantastic grades, huge tons, and definitely one would like to find another one of these. Cerro Verde, much the same story in Peru, where the purple pipes shown there on the sections are the tourmaline breccias. They're carrot shaped. This is what some of them look like. Once again, they don't appear to show a lot of characteristic decompressive or shingle type textures. Other examples, Productora. This is a nice example from Chile, from Escalon's 2016 publication. Very nice, well-developed tourmaline breccia pipes, carrot-shaped. For those that are interested, can refer to her very detailed paper in economic geology. And in Argentina, the newly emerging Filo del Sol copper gold porphyry system, which is absolutely gigantic. And this is going to be, this is really a great story unfolding. There are tourmaline breccia gold-bearing copper tourmaline pipes in this area, and particular Los Helados, where there was a PhD thesis done not too long ago. That's what the area looks like. This is from Guittart's thesis, and once again, we see nice carrot-shaped tourmaline breccia pipes. Oh gosh, just a minute. Oops. Okay, I think I'm back on track. Yep, sorry. So this is what some of the breccias from Los Helados look like. Very similar to the previous examples. Yet another example from southern Ecuador is Lumina Gold's Conejos project that has very significant tourmaline breccia pipes. And in fact, the breccias host most of the mineralization. Same story, carrot-shaped. And just to illustrate that it's not just porphyry systems, there's many tourmaline breccias associated with tin tungsten systems. That's another story, but some of the principles are similar. This is from a large tin tungsten deposit in eastern Kyrgyz, Ushkoshkon, and the breccias there are also carrot-shaped. That's what they look like. It could be a tourmaline breccia from practically anywhere. Now to go to what I refer to as the non-porphyry copper breccias. These are much smaller and they have very different characteristics. Stuart Simmons did his PhD in the Washington area in Sonora on the breccia pipes there. Very prominent outcrops as shown in the upper left slide and to the right, and an inverted cone shape of the breccia. Polymetallic, copper, tungsten, bismuth, gold, silver. Some underground photos that Stuart kindly sent me. Well-developed shingle textures and matrix mineralization. The Inaguan pipes also from Sonora. This is another copper tungsten breccia pipe system. Nice inverted cone-shaped breccias. And the same thing around Kumababi, where I visited many years ago. Copper moly pipes. Some pipes were tourmaline bearing, some weren't, but overall they're inverted cone-shaped. The same thing at San Jorge in Argentina, which is a porphyry gold copper system. So tourmaline breccias are capable of hosting copper moly mineralization and also copper gold. If we go back to San Francisco de los Andes, it's very obvious there that the overall geometry of the pipes is an inverted cone shape, as is many of the pipes around Soledad. This is the Paloma East Breccia pipe, and it's an absolute classic. The surface plan dimensions are relatively small, and then with drilling, the pipe continued to expand with depth. I talked a little bit earlier about at which levels of the pipe you might be looking at. And so with careful observation of the class composition, textures, and particularly the host rock stratigraphy, I think it's possible to develop a broad guide as to where you might be looking at the top, middle, or perhaps bottom of a breccia pipe. And clearly where you want to be is the upper part. Size does matter. This is a plan view of Tokopala, which is just a gigantic breccia pipe. It's 1.5 kilometers in its dimensions. It's actually pre the porphyry copper mineralization, but if you were in the field and you came across something this size, there's a couple of things that would strike you. One is that most likely this is clearly related to a porphyry copper system. And secondly, because of its sheer size, you're looking at the upper part of it. And so from a drilling perspective, you would expect these breccia systems or pipes to be carrot shaped, and that would have some impact on how you might design your drill program. A couple of slides that Rowan Wolf has been working on, and Rowan's the CEO of Tourmaline Metals, sums up quite nicely from an exploration perspective some of the things that are important and some of the errors that can be made perhaps in looking at the non-porphyry breccias. And that would be, as I mentioned earlier, perhaps drilling down the barren center. You want to be drilling across them. You don't really want to be in the pyrite zone, obviously. You want to be in the copper polymetallic zone. And frequently, Tourmaline breccias have been used as vectors for porphyries at depth. And I think this is a very common misconception. And one could save a lot of money just simply by looking carefully at the characteristics of the breccias and then trying to understand whether or not or how they are related to a porphyry system or not, because I think it's possible to distinguish that. From the drilling perspective, this is from the Cabeza de Vaca district. It's just prolific in terms of breccia pipes. There's some copper mineralization. It looks to be at a fairly deep level because a lot of the pipes are around or within their precursor intrusives. And so the interesting part of the pipes would be actually not the black tourmaline outcrops, but the leached, oxidized, gossinous material that would represent or come from the margins of the pipes. So just to conclude here, a couple of slides about what I think are the characteristic features. In general, there will be exceptions to these. It's just a general guide, but for the non-porphyry breccias, tourmaline breccias, I think they may form at a deeper level in the crust compared to a typical high-level porphyry system. They definitely, in most cases, have downward or inverted cone-shaped geometries. They're much smaller tons, but can have really nice grade. And they have characteristic multi-element signatures. They invariably display decompressive shock and shingle textures. There doesn't appear to be associated porphyry stockwork type mineralization or diatreme complexes. They don't seem to transition at depth into quartz stockwork porphyry mineralization, and they tend to be, the basal parts tend to transition into potassic altered intrusions with weak disseminated copper mineralization or none at all. But it seems to be typical for disseminated copper mineralization at depth. And is this style of mineralization an economic target at depth? I don't think so. To the porphyry-related tourmaline breccia pipes, in contrast, they appear to have formed at much higher crustal levels. They invariably have upward flaring geometries. They have characteristic copper moly and sometimes gold signatures. Rarely do they have enriched precious metals or some of the other polymetallic signatures such as arsenic and bismuth. Invariably, they're associated with a major quartz stockwork event. They rarely seem to display decompressive or shingle textures, and they have class of porphyry vein type or altered intrusive porphyry mineralization. Anhydrite's very common at depth, and they can be extremely big systems with less focused mineralization, and they often have porphyry copper stocks and diatremes. So just to a final comment is that I guess really from the Tourmaline Breccia perspective, the giant or the Olympic dam of the porphyry-related Tourmaline Breccia systems is actually the Los Bronces Andina Los Sulfatos complex district. That is just orders of magnitude above anything else that's known, and therefore it may be one-off, but certainly in terms of an exploration target, everyone, of course, would love to find one of those, but it doesn't preclude, I think, potentially economic targets for junior or mid-tier companies, which would be the smaller non-porphyry related breccias that are capable of very high grades. And in fact, one example being that founding mine of Phelps Dodge. So this is a table I just put together. It's a summary table. For anyone that's interested, you could look at that in your leisure. And I'd be very happy to communicate with anyone that's interested. As Peter said, the presentation will be on the web. And so I think that's about all. And I would be happy to take any questions. Thank you very much.
Oh, thanks, Doug. That was a fantastic talk. We've got.
And sorry for the rocky start. My apologies.
No problems.
It's a sign of senility and old age.
I'm sure that's not true. That was pretty sharp. So there's a couple of questions coming through. If anyone else has got one, please start typing furiously. But as always, because I've got the power, I'll kick them off. You showed quite a few photos of core with sulfides in the matrix, and there were a couple of pictures there with the sheeted veins on the side, which looked barren. Would it be fair to say all the copper mineralization or the sulfides came in as a late phase, or are there multi-phase pressure pipes as well?
That's really an interesting thing to comment on, because it would seem that the mineralization is one of the last things to happen. But having said that, it must very closely follow the brecciation event, and specifically the decompressive shock, because what one often sees are sections that are frozen in time. And so the decompressive shock textures frequently have very high grade mineralization in the matrix. So for me, that implies a very close relationship between the drastic drop in pressure and the transition from volatile to hydrothermal conditions and deposition of the mineralization. Something else that I have observed, or really haven't observed, I guess is a better way to put it, is multi-phase events in any single pipe. It is possible to have mineralized clasts, which implies more than one event, but I have yet to see an example where there's clear evidence for several breccia pulses that are mineralized in any one particular pipe. That would be very unusual. Of all of the pipes I've seen, the pipes vary from individual to individual, but within one specific pipe, they seem to be single shot events.
Okay, so even when we have, I guess, some gold and silver and other metals, they're also in that one event? Yes,
yeah, there's a paragenesis clearly, and that was as shown in the table from Soledad, but the timing of the mineralization, I think, is a fairly quick event. So rather than time gaps in mineralization, significant time gaps, I suspect that it all happens fairly quickly.
Okay, I think so. And looking at the photo you showed of the Soledad area with the multiple clustered pipes, what looked like it was a fairly short distance. Would that suggest that there's one large intrusion at depth with multiple Breccia pipes, or are these all potentially separate injections and separate pipes?
I think probably a little bit like the fingers on a hand, so that I think one cupola produces probably one pipe, but if you have a lot of cupolas, and some of them have mineralized volatiles and fluids and some don't, each one of those cupolas is forming an individual pipe, and depending what's in the cupola, I think will dictate, of course, what's going to be in the pipe. But as to why some are mineralized and why some aren't, that's something I really don't have an answer for. And in fact, one can look at porphyries, pencil porphyries, and say, well, you know, some are mineralized, some are well mineralized, and some have very little. So I think it's just what's in the cooking pot at the time. But I don't envisage one principal source that would form a whole stack of Breccia pipes. It just doesn't seem to make sense to me. So I think you've got a like the fingers on a hand and perhaps pistons, you've got these things going off at relatively narrow time frame intervals, but more than one event.
Okay, thanks, Doug. A couple of questions from the floor. We've got one from Kylie Prendergast. Would EM be effectively to quickly define massive charcoal pyro?
Yeah, good question, Kylie. Chicana are presently using geophysics to look for some of those really high-grade intercepts. Historically, it hasn't really been applied that much, but I think where you've got really high grade and it's close enough to surface, I would say that, yeah, definitely it would be worth applying, because if you find, you know, tens of meters at 10 or 20% copper, that's significant.
Yep, absolutely. Question from Ian Bruce. I guess he asked if you had time. Could you go into exploration methodologies for the Breccia pipes versus porphyry targets?
I didn't quite catch the question, Peter.
Could you go into some exploration methodologies for Breccia pipes versus porphyry targets or other similar?
Oh, okay. Yeah, they actually seem to occur together in the same provinces. Southern Ecuador is a really good example where there are some quite good copper gold porphyry deposits, and at a provincial scale there are also the polymetallic high-grade pipes which are being exploited by thousands of artisanal miners. So they can occur or seem to be able to occur in the same province, not always, but size is one discriminator for sure, because if you are looking for porphyry copper deposits, I think Tourmaline Breccias will only be a small part of that story. You would have all the other vectors that you would use for the big porphyries, the geochem, the geophysics, just the basic geology. Having said that, I've found in the past, providing there's reasonable exposure, that just simple topography and aerial reconnaissance is capable of locating. If you're in a region where you think there might be the polymetallic pipes, in theory they should outcrop very prominently, and you can actually do this off Landsat, and we've done some of that in Argentina, where you can have a good look at Landsat, and with a somewhat experienced eye you can draw circles around areas that look suspicious, follow up from the air, and then subsequently on the ground, and often that will lead you into interesting clusters of pipes. But there's no substitute for boots and hammer, by the way, but yeah.
Absolutely not. For a blind pipe, to find those, would they have a large alteration footprint compared to the size of the pipe, or geochemical dispersion?
Yeah, it's from our experience, both at Soledad and to a certain extent San Francisco, there's a wider zone of sericitization that sits above some of the blind pipes. And whilst it's not geochemically very interesting, what you're looking for are the crackle breccias relatively intense zones of ceratization, and perhaps plus or minus tourmaline on the fractures. So they do have a signature. What it doesn't guarantee you just how significant the mineralization might be below, but they do seem to have a surface expression that above a blind pipe situation. But also, having said that too, the host rock composition is also has an impact on that.
Thanks, Dave. Final question to Laura Maxwell. Have you come across any Cuprian tourmalines in your travel? Like
I'm sorry?
Cuprian tourmalines?
Cuprian tourmaline.
Or have you been predominantly focused on metals?
No, well, the chemistry of the tourmaline I haven't actually studied. I've read quite a bit about it, and as a mineral collector, I've always been interested in anything that's different or interesting. No, I haven't. Cuprian scheelite, yes. And in fact, the Tourmalina pipe in Peru had some absolutely classic scheelite mineral specimens. But Dave Cook would be the person to contact about chemistry of the tourmaline. So I've read a bit about it, and there does appear to be iron-rich assemblages and other combinations that you can use in the tourmaline compositions themselves that would vector you towards where the center of the or towards a pipe. That has some application for sure, but in terms of a mineral Cuprian tourmaline, no, I haven't seen anything like that.
Oh, excellent. Well, I'm mindful of everyone's time. Thank you very much, Doug. That was a fantastic talk. On behalf of the AIG and on behalf of all the attendees, I'd like to thank you very much. And
most welcome. My pleasure.